All right. So how should we start? Right. We're going to need to find the reaction forces at A and B because they're going to be part of the shear diagram and they're going to affect the moment diagram. In order to find the reaction forces at A and B, what are we going to want to do first? Right. We're going to want to reduce or replace the force, the distributed load between, let's call this C. Let's try that again. Between C and A with a point force, and we're going to want to replace the distributed load between A and B with a point force. Let's make a note on that here. So 1, replace distributed loading with point forces. Okay, so let's start with the one between A and B because I think it's going to be easier. What's the magnitude of the force, single point force? It's going to be the area of this graph, which is going to be 6W. So it's going to be 6W down. Oops. That stand out a little bit better. And where is that force going to act? Halfway between A and B, so 3 feet from A or 3 feet from B. All right, so we've replaced this part of the distributed load with a single point force. Now we're going to replace this part of the load. What's the magnitude of that force going to be? Right. It's going to be the area of the triangle, which is going to be 1/2 base, so that'd be 3 feet times the height, which is W. So 3W, and where is it going to be located? Right, 1/3 of the distance from the straight edge, so that would be 2 feet from A. So we'll place that one about here. And we'll call that one 3W. Let's call that FAC, and this one FAB. All right, so we've replaced the distributed loads with equivalent point forces in order to calculate the reactions at A and B. What's the nature of the reaction at A? This is a roller, so it can only be a normal or a vertical force, normal to the flat horizontal surface. So the reaction at A is going to be a y component only. B is a pin joint, so it could have an x and y. We'll draw both of them in so it's fully constrained, but I think we can all see that the x component is going to be 0. Because there are no other horizontal forces. Call that AY, BY, BX equals 0. So our step 2 is to find the reaction forces. All right. How are we going to do that? Equations of equilibrium. So we could start with a moment. We could do moments about A or about B or about C, but A or B is going to be easier because one of our unknowns will disappear. Which would you rather do? A? Sure, it doesn't matter. So sum of the net moment about A equals 0. So if we move from left to right, the first force that we have that's producing a moment about A is this FAC, which is 3W, and it's 2 feet away from A. So it would be a moment of 6W, and would it be positive or negative? Positive, because it's counterclockwise. So I'm going to write that as 2 feet, 3W. Again, moving from left to right, we then get to AY, which produces no moment because it's through the point A. And then we get to FAB, which is 6W, and it's 3 feet away. Positive or negative moment? Negative. So it'd be minus 3 feet times 6W. And then last we would get to B. And BY is up and 6 feet away. So it'd be a positive moment, so plus 6 feet times BY. All right, so from that you should be able to solve for BY. So we should be able to do this without a calculator. This is going to be 6 minus 18 is negative 12 plus 6 times B. So B is going to have to be plus 2, or 2W. 2W. Okay, and we could do moments about B to find AY, or we could just use the sum of the forces in the Y direction. That's going to be AY assumed to be up. Has to be up. Minus 3W minus 6W plus 2W. So AY is going to be equal to 7W. All right, so we've found our reaction forces. I've cloned this page so we can just go and put those forces over here. Oops. We had AY equals 7W. BY equals 2W. All right, so if we're going to do the shear and moment diagrams, first we're going to want to write the equations of this distributed load, because the area under this distributed load is going to give us our shear diagram. What's the equation of this straight line? Okay, well the slope is going to be the rise over the run. So the rise is going to be W, and the run is 6. So it's going to be W over 6 x, but the force is down. Even though this has a positive slope, the force is down. So we should have a negative in here. I'm just going to make a note in here. But the reason why the negative sign is there is the force is down. So that's, for the first 6 feet, that's the equation of the distributed load. What about for the second 6 feet? Wx equals, it equals negative W, right? It's a constant function. It's downward, so it has to be negative. And it's this value here. All right. So let's go to the shear diagram now. What color were we using for the shear diagram last week? Blue. Okay. So what's the shear diagram going to look like for the first 6 feet? What's it going to start at? What value is it going to start at? It's going to start at 0 because there's no support reaction out here. And the area under this curve is going to start at 0 no matter what the shape is. And then it's going to increase. What's the shape of the graph going to be? Parabola. It's going to be opening up or opening down? It is going to be opening down because of that negative sign here. So the area, it's going to be a negative area because it's a negative distributed load. So it's going to be a parabolic area that looks like this. And we could figure out the equation of that area. So v as a function of x by taking the integral of this function. The integral of this function is going to give us the area. What's the integral of negative w over 6x? Nope. Negative wx squared over 12. Right, because we have to divide by 2 again. Negative wx squared over 12. That's our shear diagram. So what's the value of the shear at this point? When x is equal to 6 feet, x squared is going to be 36. So it's going to be negative 3w. All right, so far that's our maximum shear. Then we reach AY. What happens to the shear diagram? Nope. It jumps. It jumps up because this is an upward force. Jumps up by 7W. So it goes from minus 3W up to 4W. All right, and then what happens? Right, and then it's the area under this graph, which is going to be decreasing, because this is a negative function, decreasing linearly. So we're going to have a straight line, going to have a slope of W, so this V of X is going to equal, well, it's going to equal negative WX, but when we integrate, we also have a constant. So that constant is going to have to be something that makes this value here 4W. So when X equals 6, this is going to have to be 4W. So what's the constant? It's going to be 10W. So C equals 10W and V of X equals 10W minus WX. Or we could also go to 10 minus X times W. If we follow that graph for another 6 feet, what's this value going to be? Negative 2W. So our check at the end is, does this last reaction force bring it back to 0? And it does. There's our shear diagram. We didn't actually have to do any calculus. I mean, we did do the calculus to come up with the equations, but we were just doing areas of triangles and areas of rectangles. To get the area of this x parabolic figure here, we would probably want to use calculus, although we could still use the table of areas in the back of the book if we didn't want to integrate, but since it's an easy function to integrate, that's probably how we would do it. So let's move on to the moment diagram now. Oops. All right, and we'll do the moment diagram in purple. Oops. What's the moment diagram going to look like? What value is it going to start at here? It's going to start at 0. And the moment is going to be the area under this graph. So this graph is all negative. So its area is going to be negative. Sorry, this is bothering me. It's not quite horizontal. There. So we're going to start at 0, and it's going to be the area of that x parabolic area. It's going to be some kind of a cubic. We could figure out that function, again, simply by integrating this function. So m of x negative wx cubed over 36. So by putting in x equals 6, we can figure out what this value is right here. So that's equal to negative 6w. Okay. Now, what happens at the point load here? Does it? If this was the shear diagram jumps up at a point load because it affects the shear. The only thing that makes a moment diagram jump up would be a couple moment that's applied to the beam. So if this was a fixed joint and it was applying a moment, then it would jump up. In this case, there is no fixed joint. There is no couple moment. So it's continuous at that point. Its slope is going to change, though, for sure, because this represents the slope of the moment diagram. So it goes from here, where it's a negative slope, to here, where it's a positive slope. So it's a positive slope that's decreasing until this point. At this point, the slope of my moment diagram is 0. So that means that's going to be a local minimum or maximum. And then it's going to continue to decrease, so it's going to end up with a negative slope. So what's that shape going to look like? It is going to be parabolic. So it's parabolic opening down again. So in order to figure out where to put this vertex, I'm going to have to figure out how much area there is in this triangle so that I know how much higher it is to put it here. So I know whether it's above the x-axis or below the x-axis. And also to figure out the area of this triangle, I'm going to have to figure out where this crosses here. So we go from 4w to negative 2w. How far is this? It's going to be 4 feet, and this is going to be 2 feet, just by similar triangles. So 1/2 base times height, 4 feet times 4w would be 16w. Half of that would be 8w. Area of the smaller triangle is going to be 2 feet times 2w would be 4w. Half of that would be 2w, and it's negative. I've written that in purple because those are the values we're going to use down here. So that means between here and 4 feet, let me just extend that line down. We're going to go up by 8w. So we're going to go from negative 6w up to positive 2w. And then for the last little bit, we're going to go down by negative 2w, so we're going to finish at 0. which is, again, our check. So this is going to be a parabola. It's going to look something like that. Then when we shade that in, it's going to look like that. So where's my maximum bending moment? Well, it's going to be at 6 feet, and it's going to be 6W. The sign doesn't matter. And our maximum bending moment must be less than or equal to 30 kip feet. Okay, where's our maximum shear? Maximum shear is also at 6 feet, and it's going to be 4W. And 4W is going to have to be less than or equal to 8 kips. So from the shear, we would have W is less than or equal to 2 kips per feet. And from our moment diagram, we would have W, oops, switch colors. W is less than or equal to 5 kip per feet. So which one is limiting? Shear. Shear is limiting. Let me just circle those so that they stand out a bit better. All right. Any questions on?
At 6 feet, there's 2 different shear values.
Yep. The shear diagram is discontinuous at A. And that's because there's a point load. So the point load causes it from jump from negative 3W all the way up to 4W. So it has both values at A. The point load isn't exactly a point load because there's going to be an area of contact that's going to be a finite width. So over that finite width, it's going to go from negative 3W to 4W. It's not going to be exactly the same point, but we're modeling it as if it is exactly the same point. So it's discontinuous and has 2 values at that point. So that's a good question. And the same thing when we have a couple moment acting on the beam, then our bending moment would be discontinuous at that point, and it would have 2 separate values at that point, even though it would actually be changing over a very small finite length. All right. So this is probably about as hard of a problem as you would get with it. Well, no, actually that's not true, because we could have distributed loads like this and then put other point loads on as well. I should look at my notes. But as long as we can follow some we don't even really need to use the calculus, but if we can follow calculus of polynomial functions, we should be able to do it. We can also do it just by areas and slopes, which is really all calculus is. There is, yeah.
I lost content.
Okay, just a second. I'll try and get you back. What looks blank? Still blank? Oh, no, now we lost Campbell River completely. So they'll be back in a couple of seconds, and they should have content back.
Dennis,
Yep.
can I ask you just on the shear diagram, where you said 4 feet to similar triangles, what was the other triangle that you were referring to?
Okay, so these, have you got content back in Campbell River now?
Good.
Yep, okay, good. So these two triangles here are similar, because this line that goes through them is the same slope. So if this is 4 and 4, then this is 2 and 2. So we knew that they were similar triangles, so because this had a height of 4 and this had a height of 2, we know this one had to have length in proportion, so this had to be 4 and 2 as well. Okay? So now we're going to go a little bit off-label. So we're going to learn another method for doing shear and moment diagrams that isn't covered in your book. But a lot of the times it makes the problem a lot easier, especially a very complex loading. We could have done the one that we just looked at. And this is a method called superposition. So what this does is it takes a complex loading and then it breaks it down into a number of simpler loadings. So if we've got a distributed load and a point load, well, we analyze the shear and moment diagrams and the support reactions if there's just the distributed loading, and then we would do it just for the point loading, and then we would add those together at the end. That's the principle of superposition. Superposition also works. I mentioned before that we could also go to the next step and integrate a couple more times to figure out the deflection, and superposition also works for that. So it actually saves a lot of time when you're doing complex loading to figure out deflections. And for most common loadings, all of the values are tabulated. So you don't have to figure it out. You just find the graph or the table. It's kind of a combination between a graph and a table. And you put the values in. So we've already looked at two methods to sketch shear and moment diagrams, one based on calculus and one based on arbitrary section at a distance x from the end in each section of the beam. And both methods yield satisfactory results, but for more complex loading, the calculations can be tedious. Another method is to break the beam loading down into a number of simple loadings. Total reaction forces are the sum of the reaction forces from all of the simpler loadings, and the shear and moment diagrams are also simply the sum. And if you move on to deflections, they are also simply the sum. Oop, and I forgot to blank out. So what we're going to do is we're going to take this loading. This beam has a point load at 1.5 meters, and then it has a distributed load between 3 and 6 meters. And we're going to replace that with two different beams. One of which only has a point load on it, and the other one only has a distributed load. So basically what we're saying is that this equals this plus this. So as an example, we're going to draw the shear and moment diagrams by principle of superposition for that loading. Before we do, I'm just going to back up to here. We're going to figure out our support reactions. So we're going to figure out the support reactions on the first one as if it's only the point load here. So if it's only the point load, how am I going to figure out the support reactions at A and B? Right. Okay, so if we do, how much room have I got here? Not a lot. If I do moment about B, if I do moment about A, then I'd have 12 kilonewtons times 1.5 meters negative plus By times 6 meters equals 0. So from that, we could easily figure out By is going to be 1/4 of the 12 kilonewtons. So that would be 3 kilonewtons. Then we could use some of the forces in the y direction, and we could fairly easily see that Ay is going to be 9 kilonewtons. Okay. Then we're going to go to the beam. Same beam, but it only has this distributed load on it. If it only has that distributed load on it, how are we going to figure out the support reactions? What's the first thing we're going to want to do? Right, we're going to replace this distributed load with a single force at C, which is going to be how much? It's 9 kilonewtons per meter over a total length of 3 meters, so 27 kilonewtons. And it's acting 1.5 meters from B. So if we do moments about B, since that one's closer to B, we can figure out what Ay is. Ay is 4 times as far away from B as this point load, so it's going to have 1/4 of the force. So 27 kilonewtons divided by 4, 6.75. And By, by sum of forces in the y direction, would be 27 minus 6.75, or 20.25. Okay, so from those two, we can figure out the support reactions at A and B on the whole beam. So Ay is going to be 9 kilonewtons plus 6.75 kilonewtons equals 15.75 kilonewtons. I don't really like where I put that. And By is going to be the 3 kilonewtons plus the 20.25. 23.25 kilonewtons. Okay, for our shear and moment diagrams, I don't even really care about those. I probably do need to know them for further design work, right? Because I need to know what size of pin, what material of pin needs to be supporting this, what kind of roller needs to be supporting this. But for the shear and moment diagrams, I don't need them. I just need these so that I can draw the shear diagram for this loading and the moment diagram for this loading and the shear and moment diagram for this loading. All right. So we're going to draw the shear and moment diagram by principle of superpositions. That means we're going to have 3 shear diagrams, which I'm going to superimpose on each other. I'm going to do them in 3 different colors. Oops. So if we do the shear the shear diagram just for the point load, and we'll do that one in, what color should we use? Do that one in red. So for the point load, what value of shear are we going to have to start? It goes instantly from 0 to 9. Right? So we go from 0, better not go too high, to 9. And then what happens between A and this point load? Nothing. It goes straight across. So that is 9. And then at that point, we have a negative 12. So it's going to go from 9 down to negative 3. And then what's going to happen? Nothing. Well, it's going to go straight across at negative 3 all the way over to the reaction at B, and then it's going to go back up. Oops. So this is point load. All right, so we're going to switch colors and draw the distributed load. So the distributed load starts at what value? Well, actually, it starts at 0 and then jumps instantly to 6.75. I should have written that point load right. And then what happens from that point? Right, the shear force does not change because there's no distributed loading and there's no point loading for the first 3 meters, right? Because we're looking at this diagram now. So nothing happens for 3 meters. And then what happens? It goes down at a constant slope of negative 9 kilonewtons per meter for 3 meters. So it goes from positive 6.75 6.75 to negative negative 20.25. Negative 6.75. Sorry, that's positive 6.75. And negative 20.25. So the actual shear diagram for this loading isn't either of these. It's going to be the sum of the two. So if I have the sum of the two, let's pick another color. Let's go with black. So that means we're going to start here at 15.75. And go straight across. What's going to happen at that point? It's going to drop by 12. So this is 15.75. So if we drop by 12, that's to 3.75. And then what's going to happen? It's going to go straight to the right until we reach here. And then it's going to decrease at steady slope. The same slope as before. So it's going to reach a final value down here of negative 23.25. And this is total shear. So here we see the 15.75 and the 23.25. Those are our support reactions that we calculated before. We didn't have to calculate them. They come out of the shear diagram. All right. What about our moment diagram? Oh, we do the same thing. Okay. I'm going to skip ahead because we're kind of doing, we're using superposition, but we're not really using the benefit of superposition. So the benefit of superposition is the fact that common loadings are tabulated. So we don't have to figure all of these out. We just plug in the numbers. So the real value of superposition principle is that most standard loadings have have shear and moment diagrams which are predictable shapes with maximum values and positions that can be determined from a few values in the problem. So we're going to come up with the standard shape for this uniform distributed load, and then we'll see how it compares with tabulated values. So this is a distributed load, uniform distributed load, W units of force per unit length, and length L between the supports. What's the support reaction going to be here? Right. The total load on here is going to be W times L, and it's going to be evenly split between the two supports. So this is going to be WL over 2 and WL over 2. So what's the shear diagram going to look like? Right, it's going to jump up to WL over 2 instantaneously from this reaction force, and then it's going to be going down at a uniform rate, so a slope of negative W. And it's going to cross here at L over 2. And then it's going to go back up here to 0. Okay, so the maximum shear for the distributed load is going to be at the ends. At each end it's WL over 2. At the center it's going to be 0. Where's the maximum moment going to be? The maximum moment is going to be at the center, right? Because we can see moment's going to start at 0 because there's no reaction moment at A or B. And this is going to be an area that's increasing to this point, and then the area is going to be decreasing. So my moment diagram would be a parabolic shape with a vertex right there. All right, what's the maximum moment going to be? Almost. The maximum moment is going to be the area of this triangle. So the area of this triangle is 1/2 base times height. So 1/2 of the base would be L over 4 times the height, which is WL over 2, so that'd be WL squared over 8. So for this loading, we know the maximum moment's going to be at the center. It's going to be WL squared over 8. Maximum shear is going to be at the end. It's going to be WL over 2. If we look on the next page, this is a really old diagram out of a really old textbook. And our uniform load is actually this one, number 4. So here they're showing the shear diagram, which looks exactly like the shear diagram we had, maybe not as pretty. And they had the maximum shear is L over 2 times W. Maximum moment is 1/8 WL, that should be WL squared. And this D here is the displacement. Since I made these notes, I found a much better source of shear and moment diagrams. And I've posted them on the Learn site, and I'll put the link in the notes that I send to Jim for College of the Rockies so you guys can find these. Just bear with me for a second. I couldn't get my computer to connect wirelessly before the class, so I didn't have a chance to find the site ahead of time. It is in here. So web links. Beam formulas. This is a fantastic site. So for a simple beam, we'll just zoom in on this. Here's what we were just looking at. Do I zoom in? So the reaction here, which is also the maximum shear, is WL over 2. V is a function of x. So that gives the equation of this straight line. Maximum moment, they tell you where it's at. Moment is a function of x. It's going to be the equation of this parabola. So that's good. What if it's only a partially uniformly distributed load? Well then, based on the parameters of the problem, we can still figure out what the maximum moment is. We can figure out where the maximum moment is. We can figure out the moment as a function of x. We can calculate shear as a function of x, where the maximum shear is. These are all for simple beams. There's also ones for overhang beams and cantilevered beams. So a cantilevered beam is fixed at one end and then just free at the other end. So an overhang beam would have the supports not quite at the ends. All kinds of different loading. Here we've got two different distributed loadings on here, which we could come up with by superimposing two of the other loadings, but they've saved us the trouble in this one. All right, so again, I'll put the link on this. This is a good way of checking your answers. If you're doing your assignment and you're coming up with curves using the other methods, try this as a shortcut. Well, not a shortcut, as a check. Just want to find... The link to this is on Blackboard, yes. And I'll put the link in the notes so that College of the Rockies can find it as well. All right, so let's go back to our notes now. So we're going to use those tables from that website to do this sample problem. So we're going to draw the shear and moment diagrams using the principle of superposition. We've got a distributed load. I'm not going to calculate the distributed load. I'm just going to go to the table and find the equations for the distributed load and put in the appropriate values, and for the point load. So which one do you want to look at first? Point load? Okay. So we're going to go back to our website here and find the point load. So far these have all been, all right, here, concentrated load. That's the one we want right there. Oh, the other thing that you'll notice in here, and this is really useful, is they give you the deflection of the beam as well. So they've gone two more integrations to find the deflection, and they also tell you where the maximum deflection is. All right, so let's just snip that. And we'll put that into our solution. All right. So for this problem, our point load is 500 newtons. So that means my maximum shear that's actually the shear value everywhere. It's going to be plus or minus P over 2, which is going to be 500 newtons over 2, or 250 newtons. The maximum moment, which is here at the point of the load, is going to be PL over 4. Well, PL is going to be 500 newtons. L was 3 meters over 2. So what's my maximum moment? Oh, sorry, over 4. Oops. There.
$375.
375 Newton meters. Okay, and that's at the point of load, so at the center. I also have equations of the moment as a function of x, and also the deflection, and the maximum deflection, and the. So let's figure out what the. I can't because I don't know the elasticity or the moment of inertia. All right. So that's basically all I can get from the point load. That's all I need. Then for superposition, we would also look at our distributed load. So the distributed load was this one. Snip that. Okay, so we have our maximum shear, which is going to be at the ends, and it's going to be WL over 2. So from our problem, W was 300 newtons per meter. L was 3 meters over 2. So 450 newtons. So that's going to be the support reaction and the maximum shear. Okay, I have equations for the shear force. It's just basically going to be this straight line. My maximum moment, this is again from the same one we derived, so it's WL squared over 8. So W was 300 newtons per meter. L squared, 3 meters squared over 8. 337.5. And that's going to be Newton meters, right? And then I have the moment as a function of x. It's basically the equation of this parabola. And then we have the deflection as a function of x and the maximum deflection as well. All right. So that gives me my values. Fortunately for both of these loadings, the maximum shear and the maximum moments are going to occur at the same place on both diagrams, so I can just add the maximum together. That's not always going to be the case. Sometimes you're going to have to take these moment as a function of x and add them together, and then take the derivative to figure out where the maximum is going to be. Or just plot it into Maple and figure out what the maximum is. Okay, so let's do our shear and moment diagrams then by superposition. Oops. So the one load in the center. Does that look like the center? Close. That one out a little bit farther. That looks pretty good. All right, so the shear diagram for the point load was simply up by P over 2, or 250 newtons. Over, down, and back up. Is that newtons or kilonewtons? That was newtons. Okay. For our distributed load, the shear diagram was a little more interesting. Right? It started up higher, but then it was just a single straight line down. So it goes from 450 to minus 450. And we'll use pale blue. Blue. So 450 would be about there. There. All right, what's it going to look like when we add these two graphs together? Nope. No, it is going to be 700, right? The 250 plus 450. And it's going to be the same slope. It's going to be the same slope. It's going to jump down, and then same slope. right, so our shear diagram is going to be this trapezoid on the left and then a mirror image of that trapezoid on the right. So we're just trying to shade that in lightly. All right, what about our moment diagram? That's going to be kind of funky looking too, because we're going to add a triangle to a parabola. I need another page. Okay, so the moment diagram. It's all positive moments. So from our point load, we had a triangular loading, which had a maximum value of 375 Newton meters. Oops. And the distributed loading had a maximum value of 337.5. I'm going to have to move that. 337.5, and it's a parabolic shape. Oops. Just going to erase that. That's going to be a little bit lower here. And more of a parabolic shape. Maximum value 337.5. And this is going to be distributed loading. I'll write that underneath. So what's the actual moment diagram going to look like? Where's the maximum going to be? Now, both of these maximum occur at the same point, which is the middle of the beam, the center of the beam. So we would just add those two values together. So that would be 712.5 Newton meters. And the shape would be the parabola added to the triangle. So it's going to be kind of like that. So sort of like a Gothic arch. Right, so it's going to come to a point in the center, but it is curving, arching up and arching down. So there's our shear and moment diagrams, and we've identified our maximum shear and maximum moment on them by combining the other two. So I think I did have one more problem on here, but there's not going to be time to complete it. What I'll do is I'll complete it in the notes before I post them and before I send them to Jim in Cranbrook. It's a cantilevered beam with 3 different point loads on it. So each of those point loads is going to give us a shear and moment diagram, which then we'll add them all together to get the shear and moment. That'll also give us the components of reaction at A. Components of reaction at A are going to be a force in the y direction, force in the x direction, which is going to be 0 because there's no x loading, and also a reaction moment, which is going to be the maximum bending moment in the cantilevered beam. All right, so I'll post that, and we'll be starting chapter 9 on Thursday. No, we do 9 and 10. Well, we do parts of 9 and 10.